Hello again, everybody, and welcome back. We're continuing example 2 in our relative motion chapter. And in the previous segment, we found you might say, the resultant velocity, the velocity of the boat to the ground, when we added the velocity of the boat to the water plus the velocity of the water to the ground. All right, but part B and C are, we're going to be changing this around a little bit. So if you recall from part A, we attempted, and I think I made this vector red right here. All right, and we attempted to aim upstream at an angle of, that's going to be 25. That's a bad place to write that. Right over here. 25 degrees north of east. Okay, but the stream was rushing south, you might say, and so it was pushing us more south than we want to go. So we found out that when we got our final vector, that was the vector of the velocity of the boat to the ground, we really only wound up going, and this is going to be kind of hard to see, that little angle I measured in there, we really only managed to go about 12.3 degrees north of east. That's that little angle right in there. Why was that? Well, because the stream is making us go more south than we wanted to go because the stream is moving south. Okay? So let's pretend for a second that you want to make the boat go directly across the stream. All right? We want to compensate for the fact that the stream is rushing south, and we want the result to be, that is the sum of the boat to the water plus the water to the ground. We want the sum of that to add up to this vector being directly across. Let's pretend on the opposite side there's a dock right here. Okay? There's your dock that you want to get to, and you want your boat to go right across. So you've got to compensate for the fact that the stream is trying to push you down, and you need to aim your boat in such an angle that you go straight across. That's what we're trying to figure out right here, all right, in part B. All right, so part B is what angle is required to go straight across. So we want the result to be, or you might say we want the sum of this vector at some unknown angle. It's no longer 25 degrees, because 25 degrees will give you the result in this 12.3 degree angle. It's some new angle right here, this red vector is going to be at. This plus the water going due south is going to result in our boat going directly across the stream to the dock. That's what we want to find, all right? So let's go ahead and set this up. I'm going to take all this right here, and I'm going to shrink it down a little bit and put it right there. And I'm probably going to, in fact, I'm going to put this over here like that, all right? Like so. And then I'm going to lock that in place. All right, so let's redraw this here. All right, I'm going to redraw the stream and this whole scenario right here. All right, in fact, I'm going to redraw it below. So here is the stream, and it's going due south. Right, we would call that the velocity of the water with respect to the ground, and that's still 1.4 meters per second at, let's say, 90 degrees south. Okay. Well, here's our boat. Right. See, I'll make it red again. All right. Our red boat. Right there, and it's aiming its velocity vector, velocity of the boat to the water, because that's how fast the boat goes. It moves through the water, and that's still going to be 6.1 meters per second, but we don't know the angle. Okay, we don't know the angle. But what we do know is that we want the boat to go straight across the river. I'm going to do this. This is a different vector. I'm going to make this in purple. All right. The previous vector, aiming it upstream at 25 degrees, coupled with the vector of the water, resulted in you going upstream about 12 degrees north of east. We want for the sum of this vector and this vector to be that we go straight across, directly across, like so. All right? So, we would call that vector the velocity of the boat to the water. Okay? We actually don't know the magnitude of that vector, at least not yet, but we do know that it is at 0 degrees east. We want the direction of this vector to be 0 degrees due east. Okay? So that's what we're saying. So this angle, all right, or this vector you might say at some unknown angle, plus the vector of the water with respect to the ground, the velocity of the water, so that's, velocity of the water to the ground, is going to result in the boat actually, oh, I'm sorry, did I make that, this should be, I apologize, this is boat to the ground right here, boat to the ground, because there's an object on the ground that we want the boat to get to, right? The object I think we said was a dock or something like that, right? The dock is right here. So with respect to the ground, we want the boat to move directly across the river, even though the river is trying to move due south. Okay? So, what is B asking us? What angle is required for the boat to go straight across the river? All right, straight across the stream. So that is this right here. That angle theta is what we want to find. All right, that's why I put a question mark up here. 6.1 meters per second at some angle north of east, but we don't know what the angle is. Okay? So let's redraw this. I'm going to redraw this triangle in a little bit bigger up here, or a little more detail. We want to find out what that angle is. So we know that the boat is cutting through the water. Velocity of the boat to the water equals 6.1 meters per second. The water is flowing due south at velocity of the water with respect to the ground is 1.4 meters per second. And we know that we want the boat to take a path. We don't know the magnitude, but we do know that the direction, the velocity of the boat with respect to the ground, is going to be something, but we know it's going to be at 0 degrees east, or just due east. Okay? So, we want to find this, first of all, we want to find this angle right here. That angle theta. What is that angle theta going to be? Well, we can't really use this right here because we don't know the magnitude. We don't know how long this side of the triangle is. But the good news is we did create a right triangle, because this is going due east, this is going directly south right here. So we do have a right triangle, so that does afford us some benefits. If we want to find this angle right here, what sides do we know? Well, we know the opposite side. The opposite side is 1.4 meters per second, right? That's opposite side right here. And we also know the hypotenuse. The hypotenuse of this triangle is our 6.1 meters per second, even though we don't know the direction. All right, so that's our hypotenuse, a big old H. Ugh, big old ugly H. Big old H right here. Okay, so for theta, for our angle theta, what sides do we know? We know our opposite and our hypotenuse. So what trig function is that going to include? We know that the sine of an angle theta equals the opposite over the hypotenuse. So if we want to find the angle itself, the angle is going to be the inverse sine of the opposite over the hypotenuse. All right, that angle theta, sine -1, I forgot, sorry. That's the inverse sine, just like we use the inverse tangent, but the inverse tangent includes the opposite over the adjacent. You might say the y over the x. Well, we don't know the x value right here, so we can't use that. So we're using the opposite and the hypotenuse. So let's solve for that angle theta that we have to point the boat upstream in order for it to result in going straight across the stream. The angle of the velocity of the boat to the water, I should say, is going to be the inverse sine of, what's the opposite side? It's 1.4 over the hypotenuse, which is 6.1. And if we do our math, that'll give us the angle north of east that we have to point the boat. So what is that going to be? Inverse sine of 1.4 over 6.1. That's going to be 13.3 degrees. 13.3 degrees north of east. Okay? North of east. And that's our answer to part B. All right, so that's part B right there. Let's just give that a name. All right. So we have our angle. Theta is going to have to be 13.3 degrees north of east in order for this vector added to the vector of the water to the ground to result in the boat kind of moving at a kind of a cockeyed direction, but the boat is still trying to point upstream, but it's going to wind up moving directly across the stream to the dock right there, the velocity of the boat to the ground. So part C is asking us for, well, what is the actual velocity of the boat to the ground? All right, we know this velocity, and so this is going to be at 13.3 degrees north of east. North of east. What is the actual speed relative to the ground? What is the magnitude of this right here? We can find that out using the Pythagorean theorem. All right. So this is going to be part C. For the velocity of the boat to the ground. All right. Well, we have the other leg of the triangle, and we have the hypotenuse. So we can say that leg squared plus leg squared equals hypotenuse squared, right? Velocity of the boat to the ground squared plus the velocity of the water to the ground squared is going to be equal to the velocity of the boat to the water squared. This is our hypotenuse. The only difference is we're not solving for the hypotenuse because we know that we're solving for the one leg, for the bottom side, the adjacent leg. So we can say, all right, well, the velocity, I'm just going to continue to write this in purple because it's a pain change of colors. The velocity of the boat to the ground is going to have to be the velocity of the boat to the water squared minus the velocity of the water to the ground, right? Because that came from this side. We're going to subtract this over to solve for the velocity of the boat to the ground. Well, all we need to do is get rid of the square right here. So that means the velocity of the boat to the ground is going to be the square root of velocity of the boat to the water squared minus the velocity of the water to the ground squared. That's going to be the square root of, I'm running out of space here. What's the velocity of the boat to the water? Boat to the water, that's our 6.1, right? 6.1 squared minus, don't forget to make that a minus because we subtracted the one leg over. Minus the velocity of the water to the ground, that's 1.4. 1.4 squared. That's going to give us our actual magnitude of the, you might say, the speed with which, or the velocity with which the boat actually travels directly across the river. So 6.1 squared minus 1.4 squared. Take the square root of that. That's going to be 5.9. 5.9 meters per second. And that's going to be this right here. 5.9 meters per second. That's the velocity of the boat to the ground. So we're using trig. We're using our understanding of how vectors kind of complement each other in a right triangle. We're just doing it in the context of 1 to 2 plus 2 to 3 equals 1 to 3. That's the whole principle along which this relative motion segment functions. All right? So that's going to be it for example 2 in this chapter. Thanks for following along, and if you have any questions, please make sure you see me, and I'll be glad to help you out. Thanks for following along. I'll see you on the next one.